Okay, so this lesson was 4.5, solving polynomial equations. And I'm going to very briefly go through the first two examples. So anytime you're trying to solve a polynomial equation, you want to factor. So this first equation, this first example, remember we begin by factoring at a GCF. In this case, that would be 2x. And then we're left with x squared minus 6x plus 9. This part in the parentheses can be factored further, and it's a perfect square trinomial, so you could factor it into x minus 3 times x minus 3. Or you could write it as x minus 3 squared. Both are correct. And then you set each factor equal to 0 and solve. So we get x equals 0 and x equals 3 as our two solutions. Now this next part we talked about in class, but I'll reiterate. The fact that x minus 3 appears more than once, specifically it appears twice, means that we have a repeated solution of x equals 3. Now, whenever you have a repeated solution, this is going to cause the function to either bump or cross the x-axis at that point. So, if you have a factor raised to an odd power, which means that the solution repeats an odd number of times, then what happens is you're going to cross the x-axis at that point. Okay? You're going to cross the x-axis at, let's write it as an ordered pair, k comma 0. Then if you have a factor of x minus k raised to an even power, which means that the solution repeats an even number of times, let me just correct that, repeats an even number of times, then you're not going to cross the x-axis, you're going to just touch it, but not cross it at that point. Again, let's just write it as an ordered pair, k comma 0. And I like to use the word bump instead of touch, just because I feel like it makes more sense. All right, let's see a visual of what that means. If I was to graph this function, I know that I have x-intercepts at 0 and at 3. And I know that the y-intercept is also 0, 0, since there's no constant term. And at this point now, I'm just going to use the end behavior to graph the ends. So the degree is 3. So the end behavior is going in two opposite directions, either this way or this way. And because the leading coefficient is positive, that's my end behavior. So I know I'm going up on the right and down on the left. Now because this x minus 3, this factor, repeats twice, what that means is at 3, 0, because it repeats twice, an even number of times, we're going to bump the x-axis at 3, 0. So I'm going to bump, I'm not going to cross, and then I'm going to have to go back up. So something like that. I don't know how far down I was supposed to go, but this is just supposed to be a rough sketch. Okay? So that's basically what it means. Let's look at another example. So here I want to find the zeros of the function and then sketch the graph. We did this one in class also, so I'm just going to go through it quickly. We take out a GCF of -2, left with x to the 4th minus 8, x squared plus 16. I can factor the part in the parentheses more to x squared minus 4 and x squared minus 4, which could be factored even more to x minus 2 times x plus 2 times x minus 2 times x plus 2, which I could write in simplified form or condensed form like so. Okay? Again, set each factor equal to 0, and your solutions are x equals 2, and x equals negative 2. And because both of these repeat an even number of times, we know we're going to bump the x-axis at 2, 0, and we're also going to bump the x-axis at negative 2, 0. So now let's sketch the graph. Again, it's not meant to be perfect, just a rough sketch. We have x-intercepts of 2, 0, or sorry, negative 2, 0, and 2, 0. In this case, we have a y-intercept of negative 32, so somewhere down here. And our degree is 4, so we know the end behavior is going to be the same. So those two pictures, and the leading coefficient is negative, so it's that. So I go to my leftmost point and my rightmost point, and I graph the end behavior. And then because it bumps, I know I'm not going to cross the x-axis at either of these points. I'm just going to bump it and head back down. So the graph will look something like that. Okay, so that was the main idea there. It's a way to help us graph polynomial functions. Okay, moving on to the content that I wasn't here for. In this next example, example 3, the main idea is if you were to try and solve this equation by factoring it using traditional methods like factor by grouping or AC method or split the middle, none of them are going to work. But that doesn't mean that we can't solve this problem. It just means we need to learn a different strategy, a different method. So whenever your traditional factoring methods don't work, you should always try them first. But whenever they don't work, you have to use what's called the rational root theorem. And this is how it works. You take all the factors of the constant term, in this example that would be 20, and put them over the factors of the leading coefficient. In this case, that would just be 1. And from that, you're going to list all the possible solutions of the polynomial. Now, these are only possible solutions. So if you want to find the actual solutions, you have to test these values using synthetic division. Best way to understand it is with an actual problem. So let's just go ahead and do example 3. So again, I'm doing the factors of 20, the constant term, over the factors of 1, the leading coefficient. So positive or negative 1, 2, 4, 5, 10, and 20 over just 1. Okay, so now what are the possibilities? Well, I could have 1 over 1, which is just 1, 2 over 1, which is just 2, 4 over 1, which is just 4, and so on. So my possible zeros are these. These are the possible zeros, or we can also call them possible solutions. Okay, they're not the actual solutions. They're just possible solutions. So now I have to test them. I always begin with the smallest ones because the probability of those being the actual zeros are much more likely than 10 or 20. So I go ahead and I set up my synthetic division with positive 1, and I try that. So 3, 2, 1, none, so I don't need a placeholder. Bring down the 1. It's going to be 4. Okay, so this doesn't work because I don't get a remainder of 0. I get a remainder of 24. Okay, so now let's try negative 1. So just erase this and try negative 1. Okay, and that works. So now I'm going to rewrite this function. I'm going to rewrite x cubed minus 8x squared plus 11x plus 20 in factored form using this information. So if negative 1 was a 0, that means x plus 1 is a factor. And then the other factor is x squared minus 9x plus 20. And now the nice thing is, if you look at the part that needs to be factored further, I can use traditional methods to factor it. So I would just think of two numbers that multiply to 20 and add to negative 9. So negative 4 and negative 5. And my solutions are negative 1, positive 4, positive 5. okay? So that's how you factor a polynomial when your traditional methods don't work. And notice the factors that ended up being the real ones were 1, 4, and 5. Okay, let's move on to the next problem. Find all the real zeros of the function and then graph the function to help you narrow down the possible zeros. So we're not going to do this part. I'm just going to guide you through this. So first, you should try factoring using your traditional methods, but because there's 5 terms here, none of the traditional methods would work. So I have to use the rational root theorem. Remember I begin that process by doing factors of the constant term over factors of the coefficient. So we'll set it up. P over Q, factors of 12 over factors of 10. Now this one is going to be longer and harder because there's a lot more possibilities. So factors of 12 are 1, 2, 3, 4, 6, and 12. Factors of 10 are 1, 2, 5, and 10. Okay, now I need to list all the possibilities, so just go one by one. So I'm going to start with 1. So I could have 1 over 1, which is 1. I could have 1 over 2, which is a half. I could have 1 over 5, which is a fifth. 1 over 10, a tenth. Okay, now I'm going to do the same exact thing, but with 2. So 2 over 1 is just 2. 2 over 2 is 1, but I already have that, so I'm not going to list it again. Then 2 fifths, and then 2 tenths, which is 1 fifth, and I have that already. Okay, just keep moving down the line. So now 3. Okay, 3 over 1 is 3. 3 halves, 3 fifths, 3 tenths, and now we move on to 4. Okay, and we're just going to keep doing that. So 4, 4 fifths. I don't need any of the other ones because I already have them. 6, 6 fifths, 12, 12 fifths. So these are all the possible zeros. Okay, now obviously that's a lot to check, and some of them are going to be really annoying because they're fractions. So I would never give you a problem like this on a test or quiz because it would take you probably 30 minutes to actually do the problem. I would probably say something like, show that 3 fifths is a zero of f of x. I would do something like that, okay? So that's exactly what I'm going to do. Show that 3 fifths is a zero of f of x. So that's what we're going to start with. I'm going to set up my synthetic division with 3 fifths. So that's 10, negative 11, negative 42, 7, and 12. 4, 3, 2, 1, none, so I don't need a placeholder, so just bring down 10. That's going to give you 6, 5, negative 5. It's going to give you negative 3, so negative 45. It's 9, negative 27, be negative 20, and negative 12, 0. Okay. So now I can use this information to rewrite f of x. So f of x is now x minus 3 fifths times 10x to the third minus 5x squared minus 45x minus 20. Now, your textbook writes this factor as 5x minus 3. Both are correct because, or sorry, plus 3? No, minus 3. Because both of these equations would give you a zero of 3 fifths, would give you a solution of 3 fifths. So you could write it either way, just to address that. Okay, so now let's keep factoring. This part can be factored further. You could try factor by grouping. It's not going to work. What will work is to pull out a GCF so that I can make my numbers smaller. So the GCF in this case is 5. So I'm going to pull out a 5, and I'll be left with 2x cubed minus x squared minus 9x minus 4. And now I need to continue the factoring process with this factor, okay? So I go back to my list up here and I start testing them. Now again, there's still a lot to test from, so I'm going to help you out. One of the other zeros is -1/2, so that's what we're going to do. Set up the synthetic division with -1/2 and this factor. So 2, -1, -9, -4. Bring down 2, it's going to be -1, -2, 1, -8, +4, 0. Okay, so now I keep going. And now I have 5 times x minus 3/5 times x plus 1/2 times 2x squared minus 2x minus 8. Okay. Again, your book wrote this factor as 2x plus 1. Doesn't matter. Both give you a 0 of -1/2, so both are correct. Okay, now I need to factor this part further. So I'll start by factoring in a GCF of 2, but I already have this 5 here, so 5 times 2, 10. And then x squared minus x minus 4. Okay, now if I wanted to factor this part out further, I would have to think of two numbers that multiply to -4 but add to -1, and there's actually none of them. So this is as factored as a polynomial is going to get, okay? All right, so now I want to find all the real zeros. So I'm going to set each factor equal to 0 and solve. So 10 equaling 0 is irrelevant. Here I get x equals 3/5. Here I get x equals -1/2. And here I can't factor, so I have to use a different method. So it's a quadratic function, so I'm going to use a quadratic formula since the b value is odd. I wouldn't want to complete the square. So that would be x equals -b, which is -1, which is +1, plus or minus the square root of -b, -1 squared, which is 1, minus 4 times a times c. So this will all simplify to +16. So I'm just going to write that. All over 2a, so 2 times 1, which is just 2. And then combining like terms under the radical, I get 17. And those are all my zeros. Okay, so the zeros are 3/5, -1/2, and 1 plus or minus the square root of 17 over 2. Okay? All right. Last example. Here, this is very similar to the problem in lesson 6. Anytime you have an irrational zero, just like anytime you have an imaginary zero, those will always come in conjugate pairs, okay? Here, we see that they came in conjugate pairs of 1 plus √17 over 2 and 1 minus √17 over 2. This will always be the case. They're always going to come in conjugate pairs. So if I want to write a polynomial that has zeros of 3 and 2 plus √5, I know that there's also a 0 of 2 minus √5, okay? So I'm just going to set it up. If I have a 0 of 3, I know the factor is x minus 3. If I have a 0 of 2 plus √5, I know it's x minus, in parentheses, 2 plus √5. And then lastly, 2 minus √5. I'm going to approach this in the same way as the problem in lesson 6. I'm going to begin by distributing the negative and regrouping. This isn't the only way to do the problem, but it's definitely the most efficient way. Okay? So I'm going to multiply out these two factors. So that will be x minus 2 minus √5 and x minus 2 plus √5, and regroup the first two terms of the parentheses. Okay? So that's going to become, when we FOIL, because they're conjugate pairs, I can skip the outer and inner part, and I can just do first and last. So first, x minus 2 times x minus 2 is x minus 2 squared. Last, -√5 times +√5 is just minus 5. And then when I multiply out x minus 2 squared, I get x squared minus 4x plus 4. and I still have the minus 5 on the outside, so that's x squared minus 4x minus 1. And then bring down your x minus 3, and now multiply those two out. I'm just going to distribute, so x into the other parentheses gives me x cubed minus 4x squared minus x. 3 into the other parentheses gives me negative 3x squared plus 12x plus 3. Combine like terms, and you get f of x equals x cubed minus 12x squared plus 11x plus 3. Or sorry, I multiplied, minus 7x squared. And that's your final answer. And that's it.